Bluwave-ai is the first company to present on that day. It is using artificial intelligence and big data analytics to enable smart grid. If we have the grid already, set the characters to enable the smart brain of it. We will start with some general ideas in this presentation and dive deep into what Bluwave-ai is focusing on. The later part will be very technical, so keep braced. Well, even for myself.
Then we're going to switch gears a little bit and talk about data enablement and how the introduction of various technologies into a grid and into the integration of renewables as resources and what data has been able to enable for us to do that. I'll go through some high-level discussion around AI in particular as it relates to different types of AI models used within our products. And then at the end, I'll give you a few ideas and use cases about where we've oriented our solutions and where we've deployed the solutions. First of all, talking about climate change, I'm pretty sure you've all seen something. How many people have seen this NASA rendering of? Yeah, so there's a lot of people who've already seen this. But if you look at the warming of the Earth, and you look at the dates up on the right-hand side, you can more or less pick out the events that happened in terms of the timing of the major heating of the Earth. So obviously, one look at this, you would come to the conclusion that the Earth is warming rapidly or accelerating, and that is exactly what's happened. The warming of the Earth has coincided really with the burning of fossil fuels and the Industrial Revolution. But it has accelerated in the last 30 years, more so than it had in the previous 60. So that's another important aspect of climate change, is that the things that we do today may not have relevance for trying to take some action against climate change for the next 20 years. So it's important that we get out early and we get out ahead of these things and take actions. Climate is changing in terms of the sea level rise. That number 3.3 is millimeters per year. And you can see that the slope changes as time goes on. This is only from roughly 1990 to 2015, 2019, kind of around this time. But you can see that the slope actually of the curve is changing, and it's accelerating at the other end. So it's getting steeper, and so that's another indication that climate change happens slowly until it gets to a tipping point, and then actually the curves of these things start to change. The other indicating factor of the impact on climate that we're having is Arctic sea ice. There used to be a lot of Arctic sea ice coverage for the whole calendar year. Now that's changed, and the Northwest Passage itself is open partially for a period during the year, which is pretty telling, and that's pretty devastating to what's going to happen in those regions as shipping traffic and other industrialization of those areas happen. Not to mention the fact that it may end up ultimately being a security risk, having to maintain that third border in a more forceful way. But that is happening. The other thing that I wanted to mention is that energy and electricity have a direct correlation to the well-being of the people within those societies that have it. There are the haves, there are the have-nots in the world from an electricity perspective. Some of it is due to the poverty of the nations and their ability to build infrastructure to support electricity being delivered and energy being delivered. The other is that it could be an oppressive regime that controls electricity as a way to oppress people. If you look at this map, you can probably pick out, if you're geography majors in the world, in the room here, can pick out various regions. But if you, let's see if I can do this. If you look over here, there's South Korea, which is pretty well lit up, And that black dot is the connection of the peninsula to China. That's North Korea. You can see that it's fairly dark. This is Siberia, this is Mongolia, this is Eastern Russia, obviously Africa. Pakistan is in here, in this dark spot here, the Amazon and so on. But you can see that great masses of population and geographies within this map are not electrified. And that is leading to a great gap between the haves that have electricity, can do things in terms of increasing their position in life, in terms of being more able to get materials to do education and so on. And so the gap continues to grow. The other is energy reliability and resiliency. So there is a call for doing a little bit more than what we currently do in terms of introducing reliability and resiliency models to build that. If you remember, in 2003 there was a blackout that was caused by a branch that fell on a hydro on a power line next to a substation transformer. Morning. Oh, thank you. I'm water rich back here. And caused a major blackout. I don't think you were impacted here. In Ontario, where I'm from, we lost power for about 4 days where I live, and some people lost power for much longer than that, some people shorter than that, so it was quite impactful. And obviously the upper Midwest and into the seaboard itself in the US lost power, so that was a major issue. We all remember the tsunami and the impact it had on the reactors, and the impact that had on the neighboring states within there, and prevailing winds bringing some of that material to the western part of North America. Again, a resiliency issue. The other challenge that we have in the next 30 years is going to be how to produce more power, more electricity, without it actually having more impact on our environment. It's a major challenge. If you look at the mix today of TGE being total global energy or electricity, the mix today is somewhere in this ratio. Fossil fuels generally generate more today than the renewable mix that we have. And really what we need to get to is something in reverse of that over the next 30 to 35 years. And so that is a major challenge of producing more and impacting less. So all of those things being said, renewables make sense. If you look at them from an impact on the environment, it is a positive impact when managed properly. I'm not saying by any means that we are promoting the complete extinguishing of all fossil fuel-based power generation in the world. At some point it may make sense to do that, but what we're saying is there are great opportunities today to introduce renewables into your environments. And whether it's a renewable from the standpoint of an enterprise, adding that as a microgrid onto their organization to try to change the way that they produce power and become somewhat of a prosumer on their own, or whether it's a utility grade renewable installation that provides you with wind and solar battery mix with conventional power to trade off the growth of the fossil fuels with the growth of renewables. So these are the reasons why we look at renewables. These are the reasons why we chose to build AI solutions around the introduction of renewables into the power generation market. This is another way of looking at it. One of the things certainly that is happening, and is happening at an accelerated rate today, is the introduction of technologies to help and ease that introduction of renewables into power generation in the mainstream. Communities and corporations have started doing those kinds of things with community power associations and with corporations putting solar, wind, and so on into their power mix. Governmental involvement, probably everybody who's been involved in the Paris Accord is already funding startups, and seed money has gone into the industry to help bring those solutions to market. Utilities certainly have recognized that there is parity in terms of the overall economics of introducing renewables into their mix with their conventional power, and have stepped up to do that. And new players are emerging. 10 years ago, you would not have seen some of the activity that we see today in the introduction of independent power producers who negotiate power production with either grid players or with end user organizations. The power gets put on the grid, and then there is a transaction that has to happen that is accounted for. Prosumers, lots of places have feed-in tariffs. I don't know if the East has had a feed-in tariff yet, but you have. But lots of jurisdictions worldwide have used feed-in tariffs. Germany grew their entire renewables markets based on very, very lucrative tariffs for producers. Energy developers and finance now is coming to help these developers to build the business cases and provide them with long-term loans to be able to install these things and not make it too onerous to be able to produce these. And then technology. So we're at a real intersection here of a variety of technologies that make this this realm that we're in now work well. A lot of the technologies that are being introduced to help you optimize, predict, control, dispatch these resources generate a lot of data, and that's the kind of thing you need. You need this big data if you want to run some very interesting models in the AI world. And so there's a real intersection of various technologies that are allowing us to do some pretty nice things with respect to introducing renewables with the conventional mix of power generation. Another way to look at it is, the growth of the renewables and where we need to get to. There's a lot of different numbers out there, and so the main point here is to use the trending of where we need to get to and where it is today. But from a pure total energy perspective, these numbers are fairly accurate. At the bottom here are some of the players that are getting involved in the energy management. So data enablement, as I was talking about earlier on, there really is an intersection here, and I ran out of space on this slide to put more terms in there. Certainly the intersection is not only these things that are happening today, but these are the main ones. AI, IoT, big data, those things kind of go together in terms of trying to solve some of the issues around how do I build applications that resonate well with the challenges that application is trying to do. And when applied to a smart grid and applied to a microgrid, it makes total sense for what we're trying to do. One of the things that's really important about generating data is that the more data you can generate, the likelihood is that you will build a more intelligent solution. So if you have an application that ingests only a small amount of data, your options for what you can do with that application are fairly limited. If you have an application that ingests great amounts of data, you very likely have the luxury of deciding through certain methodologies what you want to do with that data, how you want to parse that data, how you want to select the features of that data, and so on. So data management, pre-processing of data, when you have great amounts of it, give you a lot of options on what you want to do. One of the biggest challenges that anybody faces when they're developing AI applications, as we have found, is that it's about the pre-processing and the cultivation of the data that takes up a lot of your time. But that's the importance of it. So as you move down sorry about that, I'm learning how to use this here. As you move down the axis, you can see that, you get to a more intelligent solution, and this is where we play. We play up in this smart area here, and again, great amounts of data are generated by the various devices out there, and we consume a lot of that data and qualify a lot of that data for use within our applications. And today we're playing right here in this space, but our roadmap is here and beyond. Your metering infrastructure generates a lot of useful information, great amounts of it, at different levels within the infrastructure, be it a residential or an industrial location or an enterprise smart meter, or be it something more at a substation or something more at a relay and so on. So you can get the states of your grid. You can also get constant delivered streamed information about load, consumption, and various other aspects that are important when you're looking at applications in this space. So these are the metering devices that are typically used in your infrastructures. As I've been alluding to, it's not an easy task to go from unstructured data to something meaningful at the other end that can be consumed by your AI applications. There's really three types of data that we get confronted with, and those are unstructured, semi-structured, and structured data. Structured data being the easiest to deal with, and the unstructured obviously being the most difficult to deal with. So we run a lot of algorithms against the data to parse it, clean it, backfill data where it's needed, fill in gaps in the data. If you're doing AI models, and how many people work in AI models today in the room? If you do AI models, one of the things that throws your model off totally is if you have gaps in the data. So you need to be consistent, and you need to backfill that, and there are methodologies that I'll look at and show you that we use within our environment. So there's an awful lot of information, and more the applications are not only considering data feeds from the devices that are in the field, but also looking at other websites that may have information that they can coincide and correlate with that data. And for instance, if you have a sensor that's giving you some load or generation measurements, you may also be interested in, if it was a wind generator, you would be interested in the wind forecast. You'd be interested in the weather forecast of that day. You'd be looking at relative humidities and pressures and so on related to that, so that over time you can build a pattern of what that power generator looked like. So that's kind of here, and we do a fair amount of that. We take weather forecasts in along with our loads and generated power capability, and consider those aspects when we build our algorithms. This is where we get into, some definitions of things that you guys will hear and see more moving forward. I mean, we're all familiar with things like, oops, sorry, still learning how to use these buttons here. Things like what statistics are. And really this field is based on statistics, this entire field. Artificial intelligence is kind of an umbrella a statement that people make about a very early introduction into intelligence, which started back in the mid-50s actually. But the reason why branches of that technology are now being successfully deployed has everything to do with the speed of computers and the amount of data that we've got access to. That's the only enabling aspect that was missing till now. So when you look at our solutions, you'll see that on our solution there are two main servers. There is an edge server and there is a centralized server. The edge server has a GPU, graphic processing unit, in it to be able to absorb that traffic in real time and run the prediction and optimization algorithms, while the center trains those things. So the center runs the AI algorithms and pushes the new models down to that edge. This could not have been done without the power that is in computers today and without a great amount of data. So we concentrate on machine learning, data mining. We don't do deep learning today. We are headed there. But if you want an analogy of, kind of the difference between machine learning and deep learning, it would be easiest to say that deep learning uses a heck of a lot more data already. Machine learning uses a lot, but deep learning uses a lot more. Deep learning is not good for a small data set. The other thing is that deep learning is absolutely super intelligent and has the ability to do things that we would not do in machine learning. I'll give you an example. If you use machine learning and give it a model, it will consistently use that model and update that model to give you an output that you have desired. You trained it to give that output. So you can throw the same data at it all the time. It'll run through the data in the same process, and it'll give you the same output unless you train it to do something different. In deep learning, for instance, if you wanted to throw data at it, it would learn the shortest path to get there. So it would pick the attributes of the data that you have and say, well, the last time I ran this, I ran from 1 through 10, and I ended up making my decision in the last third of that data set. So next time I'm going to use that first third of that data set and make make the rest of it less important. So an example would be, how do you tell a difference between a dog and a cat? Well, you would start putting in things like, does it have pointy ears, does it have floppy ears, does it have bushy tail, does it bark, does it meow, those kinds of things. Eventually the deep learning algorithm will make a decision. The next time it runs through that, it'll shorten it. It'll be able to figure that out a lot faster. And so it's able to do those things and find the shortest path to the decision. We don't use it today, but we plan on using it. We are actually developing some deep learning, but we just don't have it on the market yet. I know that my the overview in the program kept it fairly high level. I'm going off script a little bit here, but I just wanted to show you a little bit of, if you're considering AI applications, some of the things that you will have to do to make AI applications run well. Pre-processing of the data is good for any type of application. So this is not just unique to the fact that I want to run an AI application. Getting unstructured data out of the field and making it consumable by applications is a major challenge for everybody. And there are steps in the process that we use where we've developed our own in-house tools that help us speed these things up. And some of them are AI-based tools that we use to actually speed up pre-processing. But like anything, there are stops in the process. Data integration, where you identify the data and you throw away the data that is not meaningful to you at all. It could be redundant data, but it may also be data that you don't necessarily need. Over here is, one of the important aspects is putting in data where you have gaps. Typically, filling in data where you have gaps. There almost isn't anything in the future from a data perspective that you can't learn by looking backwards. So one of the ways of doing that, of course, is that you can fill in those missing bits of data. If the data set is huge, it's not going to have that much of an impact. So you can fill it in with some historical data or a constant of some form. And that's completely acceptable to the algorithms. Outlier detection and deletion is anything that's completely out of the realm of the possible with regards to your data set, you will get rid of. You will not use those. They will have a major impact on your algorithm eventually. So we get rid of that stuff. And honestly, I can't side of the slide over there, but I think it's the skewness processing, where if your data is skewed, so what that means is you have a center line and most of your data seems to be off to the right or off to the left. In qualifying data, it's not easy to work on data that is not symmetrical. So what you will do is you will pull that data over to the center through a methodology, and then you will be able to do things to the data on both sides of the equation easier. And that's typically what you do with skewness processing. this one is standardization, which I think is fairly easy. So that's when you have data that is in a stream, and you may want to turn it into intervals. So you want to break it up into discrete pieces of data, and it's more relatable from that perspective, and it's easier to do binning and those kinds of things with the data. And the last one is I think it's attribute construction. So this is very important for your data when you're doing it. It's the ability for you to build attributes that may be easier to manage your data. So if you have this room and it's 15 meters long and 10 meters wide, rather than actually having to deal with those two bits of information, you may just say, just give me the area. And so now I have the area. So I've built an attribute called area. So that makes the management of the data much easier. You can cut down on the amount of data that you need to process by doing those kinds of things in attribute construction. So now we've gotten down to this point. We haven't done any AI yet from a modeling or application perspective. This is just data cleansing and the precursor to usefulness, as we call it. All data is useful. I'm not saying it's not, but it is in need of work if you want to use it for your applications. The great thing about going through a process like this is that you get a standardized standardized way of communicating that data for a raft of other applications as well. And if you've done your job and built it in a way that is satisfactory for that, the value of pre-processing then goes up by the number of applications that it can use. So it's very important to do this step and do it. So let's talk a little bit about machine learning. We'll talk about two types of machine learning that we use within various aspects of our applications. One of them is called supervised machine learning. It's really about the fact that it's trained. And typically when we go into an organization, a utility or any other organization that wants to build management of their renewables around using AI as a methodology, typically we will look at historical data and we'll build a simulated model for them so they can understand the impact that data has. And that simulated model can then be turned into a real world model and used as the training material, as the trainer for the machine learning applications. So all supervised means is that it's learning from trained data sets. So it's got a model that it refers to, and it looks to improve on that model every time. There are two types that we use, or two types that are available. I'm not supposed to tell you which one of these two we use, but you can probably guess. They are quite a bit different from one another in terms of classification and regression. Classification is a very distinct method for making a determination on something. So if you want to determine that your email is spam or it's real email, I mean that's an example of a classification of data. The other is regression, which takes target values continuously and tries to improve on those, and has the ability to run single or multiple of those variables. The interesting thing about regression from an AI perspective, of course, is that it's time series. And time series is really what prediction and optimization is about. So there you go. So supervised machine learning, this would be an example of a simplistic view of what that algorithm would look like in our modeling. We have the training set, and then we have the predictor model itself. The other interesting aspect of our optimization is that we embed various functions together. So in this case, you can see that I have a predictor model, but I also have my optimization model running next to it, which is feeding back data sets into the predictor model, which only improves the performance and improves the livelihood of the model. And so there are different model types here. Again, I won't mention which one we use, but there are a whole lot of different model types in supervised machine learning that you can use for these purposes. And the important thing to keep in mind is that although we're a bunch of data scientists, we also have PhDs who are power management PhDs, so they actually build these models with how we figure out these things for power management purposes. Applications for this: forecasting, prediction, transactive energy management. It's kind of a nice way of sort of keeping track of everything at the same time. One of the applications that we're working on is an interesting one. It's in India, where they have a main utility that has almost 100 IPP contracts at any given time that they can buy power from. There is no way that a human being at any given time can make a determination on where's the best place for me to buy my power. So we load all of those into our AI algorithm, and then we set a bunch of conditions that have to be met for certain ones to be selected. And then the AI algorithm learns over time what is the most effective way, most efficient, cost-effective way to choose the IPP at that moment in time. We then build a forecast and negotiate an SLA with those producers so that all of those aspects could be met. By building that forecast and understanding what the forecast would do, we were able to negotiate a much better deal on the power from the IPPs. So it had some really interesting roots to start, and now it's sort of growing tentacles. But that's a transactive energy management aspect. Another one would be a bunch of prosumers who have generated their own power, and they want to go through an exchange of that on a local basis. You may not want all of that hitting some kind of a long haul grid. You may want to keep it all within your LDC on a local basis. So we can actually do that transaction on a local basis, right? And trade and give among all of those producers. So this would be a predictor model. So what was inside that predictor box back a few slides is this. And basically, there's a bunch of testing that you do with your data at that point to determine that this data is good. You do a stationary test, which basically tells you, yeah, those data sets that you're running are within reason of what we believe to be good data for those purposes. One of the most important aspects, though, are things like feature selection, which is I'm going to select this data. The data has a particular aspect to it that is useful, and I'm going to eliminate data that is similar to it that is not as useful. So as you go through the selection process, you get better and better at selecting the attributes that you want. AC and PAC analysis is really about correlation of the data to the timelines that you use in a time series, and it allows you to really understand at a high level. So you take rough data that looks very confusing and you run correlation against it, and it'll give you a smooth output of that data. That's an example of how the AC and PAC work. So it's autocorrelation and partial autocorrelation, and they're not as closely related as you would think by their names. And then we do a hyperparameter tuning aspect, which is we're really good at building models, so we run a model next to it, which is perfection. And we determine whether the parameters are actually meeting that model striving for perfection, and that's how you get accuracy. All of this stuff is then fed back into the model and constantly striving to get to the outcome that we've asked for. And that's how this, this predictor would work. Another type of machine learning out there is, and I won't spend too much more time on this, but it's reinforced learning. And it's it's like teaching your dog a new trick with a reward, no reward method. So the way that and it models in there, and you can look it up, or Q learning and deep Q learning. But if you look it up, you've got basically you've got an agent that takes information from the environment, and action is performed. So you have a state that is understood. You've got a reward that is understood, and that reward is going to determine what that next action is going to be to try to change the state to meet the state requirements that you've asked for. And you'll get an action that takes place, and it'll constantly cycle here until it gets what it wants. Some applications for reinforced learning would be self-tuning control. So, you know, as you're striving for hands-off control of your environment and very little operator interaction other than monitoring, these are some very important aspects of AI that you could employ. We employ it in our approach to self-tuning and real-time optimization, obviously. So those are just some examples of what we embed within our products to make them do what they do. We've built our own AI framework, and we have built our own in-house tool sets to help us do some of this. When we're first researching and doing some things, we take a fairly simplistic view of the actual programming of the examples that we want to include in our models, and we use Python and so on for those kinds of things. But once we set it on a path for productization, it is then hard-coded, and all the things that you would normally do in aspects of turning that into a software product for the market are the things that we do with that at that point. I'm going to talk a little bit about, while I think of it as well, there's a couple of data sheets up here. They're one-pagers, fairly high level, fairly simplistic stuff. You can grab on your way out, and my business card is there as well. A little commercial message for you. Basically, this slide speaks for itself. This is really what we try to do. 5, okay, let's speed up. Never mind that one. Basically, this would be an architecture of a solution, for instance, and over here is the center, which is really the brains of it, and over here is also sort of the operational brains of it. The nice thing about doing all of that data pre-processing and making all of those efforts in making the data usable is that now the data resides in the databases that is available to any other application you want to run against it. We will have documented the formats. We will have made the formats more of a standardized model that you can use for other applications. So lots of people like us to come in and do a lot of pre-processing, run AI algorithms, and oh, by the way, make that data available for other applications for us, please. So we do a lot of that work. Yeah, so that's basically how it works. We take information from the spectrum of renewables and the renewable aspects, as well as the conventional generation aspects, bring all of that into our AI models, and then figure out the best method of doing what you want to do. In a lot of cases, people have deployed renewables and they don't use them to the nth degree. They don't get used enough, and that's kind of what we're trying to change. The other thing is a lot of people deploy batteries and they don't use the battery enough. And so we have a battery sizing exercise. We have a model building exercise that we will do with you as a service. We have a simulation exercise that we can do as a service. But one of the things that we promote mostly is we're going to make full use of your renewables and give that back to you as a savings on the import of grid power that you would normally have to do. And that's really the message. It's software as a service, so we run in the cloud. We can put the edge server on site if you determine that's what you would like to do, but there is no need to do that. But we are a software as a service prescription model. This is one example of an animated slide that actually is in play now. It's a nested microgrid controller for a utility. And basically what it does is it allows us to have multiple microgrids controlled with our edge device and have one centralized server handing the models down to those edge servers. That's one example. We did a project for Summerside PEI, which was our first sort of big publicized one, and I think we've really killed it to death with publicizing it, but it was a good project because basically what it was about limiting the import power. So they get power from off island, and they wanted to make sure that they were using their resources the most. So we were able to turn around and give them back hundreds of thousands of dollars over a calendar period, actually lots of hundreds, several $100,000. And basically what it meant was they were importing less power, they were using their resources, their local wind, and now solar, and now battery better. And that was done through AI, and that was done by being able to forecast and predict what the wind was going to be able to produce for them in terms of their wind turbines, what their loads were going to be, and to make full use of the resources that they had to make sure that they could use that first and then import the power second. They had to give a forecast back to their import power every hour. And so we forecast, I mean, we can do it on a minute basis, but we forecast that for them in advance of that so that they know what to dispatch. They know what to ask for. And the ask has continually gone down over time. This is an IPP, same deal. Basically, this particular one is Raglan Mine in Northern Ontario. And it's a good example of, the diversity of the applications that we can get involved in. Everything from a microgrid for a mine to a utility to a municipality to a campus. Again, right across the board, you could apply our algorithms. Some of our partners are missing from this slide. It's a little bit outdated. In terms of funding, we've got quite a bit more funding from various sources, government mainly. And then some of our projects over here, Tata I referred to, Hydro Ottawa was the nested microgrid, Summerside, and honestly, I can't see those over there, so you guys can. We solve renewable energy challenges in the distributed energy basis, and I'm done. Thank you. Is that 45 minutes?
Has there been, product development headed that direction so far, and how is that envisioned to play out?
Yeah, so we look at various opportunities from a product perspective with somewhat of a global view. We, although are Canadian based, there are other jurisdictions in the world that could consume types of applications more readily than we can here. And so we've spent a considerable amount of time trying to understand what that looks like and where we spend our time on productization. And really it's about, for us, it's about renewable efficiencies and control and optimization and those kinds of things. And the renewable resources that are attached to them, like a battery, for instance. What we have found from a battery perspective is that running AI algorithms with a battery in tow improves the efficiencies of that by 30 to 40% already. Certainly we have found that with a couple of organizations that we have helped them do two things. One was run a simulation with their historical data to understand the size of battery that they should be looking at to accomplish what it was that they were going to accomplish. And then by using AI with that battery, we sized that battery almost in half of what they needed. Batteries are expensive still, and so they were, very, very happy with the fact that, and it's performing very, very well today. So this is over the last year or so that we did that. But, there is an oversizing that takes place in resources when you're not really sure what the simulation output should have been. So, that's one of the services that we perform that I think helps people understand where to spend their money on resources and so on. Yeah.
With your data that you're working on, is it primarily on the generation side of weather prediction, or like how intense is the data collection and control on the load side, especially in the case where you have like a lot of residential loads?
Yeah, so it's really predicting both aspects of that. Really understanding what your load is going to do helps you really forecast what your power generation is going to have to meet. And so there's a variety of applications from a high level that we get involved in that have different methodologies for storage that impact what that utility would want to do with the excess power that they may have, and what time of day you want to do that with. So we look at all aspects of that. Anywhere we can get the data, we will look at it, and we will determine through the simulation whether the output and the outcome that they're trying to achieve could consume that data for the purpose. When you're dealing with a utility, a lot of times it is not just the smart metering data, but it can be the SCADA information and so on. So, yeah.
I do not have a lot of experience on computer programming. However, I do know the importance of data and data analysis. Advanced level of modeling and tuning like this would provide us with a better optimization, which sure improves the entire system efficiency. If the utilization of renewable energy can be increased instead of curtailed, the amount of renewables in the grid will for sure increase. Anyhow, this is a very beginning for this event. In the next video, we will see more specific topic.